When we are defining public key algorithms, we always say that their security depends on hard mathematical problems, but in order to talk about this hardness, we have to talk about the types of problems and why they are hard or how they are hard to solve. So let's start with types of problems that we are going to deal in the following slides. So actually we will divide the problems into decision and the search problem. A decision problem is a problem whose solution is yes or no. So it is a simple yes or no question. And a search problem is a problem whose solution can be more than yes or no. So it might seem a little bit obvious from the definitions, but let's see with an example why this is important. So for an example of a search problem, we can talk about the factorization problem. So given an integer n, which is greater than 0, you are asked to factorize n. So this is a search problem. You are trying to find divisors of n. So it is a search problem. But we can turn this into a decision problem as follows. Given an integer n, question is n prime? So this is a decision problem because your answer would be yes or no. So you might think, so it is obvious that when you solve the search problem, so for instance, when you factorize n, if n does not have any non-trivial factors, this would mean that n is a prime number. If it has non-trivial factors, which means divisors other than 1 and n, then we will say that it is a composite number. So we will answer the decision problem too. So solving the search problem also solves the decision problem. But counterintuitively, you might answer this question without solving the search problem. So you can decide if a number is a prime number or not without finding its divisors. So this is a very counterintuitive result actually, but this is the case. So decision problem is somewhat easier, but search problem is somewhat harder, and we will see why this is the case in terms of factorization problem. So before moving on, let's see more examples about some problems that we can use for public key algorithms or other types of algorithms. So here are some, let's say, hard problems. The obvious one which we are going to use for RSA is integer factorization search problem. The problem of finding a non-trivial factor m of an integer n, or else determine that n is prime. So this is the integer factorization search problem. Another one is the traveling salesman search problem. So in this problem, assume that you have a lot of cities in a map, and some of the cities are connected to others with more than one road, let's say, and all of these roads are either have a distance, or maybe you are spending some money for this road, so they have some price. So question is, you are asked to find the shortest or cheapest route that starts from a city A and passes through all cities on the salesman list and return to A. So if I'm not mistaken, this is known as an MP hard problem. Another problem is the tree coloring search problem. So assume that you are given a map and there are some cities, let's say, which has borders to each other. So when you are given such a map, you are asked to color every city with a color. So question is, can you color the whole map with only using 3 colors, but none of the neighboring cities would have the same color? So you have to color them with different colors so that it will be easy to understand that the neighboring cities are different cities. So it is the task of coloring vertices of a given map or a graph with just 3 colors such that no 2 neighboring regions vertices have the same color. So you might ask that why this is a 3 coloring problem and not the 4 coloring problem. Strange thing is that you can color any map with only using 4 colors. regardless of how you draw the cities in your map. So again, this might somehow might be counterintuitive, and people always say that, okay, I will draw such a map that it will be impossible for you to color it with 4 colors. But this is a proven theorem coming from graph theory, so you cannot beat it because it is proven. So you can always color a map using only 4 colors. So the question is, can you do it with 3 colors? So search problem, so if you can answer this with yes or no, then it will be a decision problem. But if you really color everything and find the solution, then it will be a search problem. So we talk about some hard problems. Of course, we are saying that they are hard, but this is not a scientific term. We are just saying that to understand. Actually, the correct term will be intractability, and we will talk about it a little bit in a minute. But now let's see a really hard problem, which is called discrete logarithm problem, and see why it is hard, and then see how we can use it for key exchange. So we will use this for the Diffie-Hellman key exchange. Of course, the hardness of this problem also affects other some of the other public key algorithms like AlGamal or elliptic curve cryptography or even RSA. So if you can solve this problem in a very fast way, for instance in a polynomial time, then all of our almost all of our public key algorithms would go to waste. So let's start with the definition of discrete logarithm problem and see why it is hard. So let G be a group and small g its generator. So actually at this point we have to talk a little bit of algebra. So a group is actually a collection of elements, and we define an operation on this group. So for instance, think about integers and the addition operation. So this is a group, and you can use the elements of this set, which is just integers, and you can add them to each other, and it will end up again in the set, and so on. So in order to be a group, you have to satisfy some properties, like the group should have an identity element, and in this case of addition, 0 is the identity element, and so on. If you, instead of addition operation, if you choose the multiplication operation, then we have to exclude 0 from the integers, because it wouldn't be commutative and so on. But the identity element in this case would be 1, because multiplying with 1 gives you the same result. So but we don't need much more about I don't want to spend time about the definition of a group or a generator and so on, but simply saying a generator means that you can use only this element and the operation that is defined on this set, and then you can generate all of the remaining elements in this group. For instance, using just 1 and adding it to itself, you can generate other integers and so on. So with keeping this in mind, but of course, it is always a good idea to check from a mathematics book or from the internet to see what a group is, okay? But assume that we have some set of elements, and we can generate this set by using a single element. And let's say that let's define the discrete logarithm problem as follows. Given A, it is feasible to compute G to the A. This means that actually you are applying the operation in this group A many times. So if it is multiplication, then we are saying that we are asking you to compute G to the power A. But if you define the group operation as addition, then this would be simply A times G. Okay, because you're adding G A many times, and this means A times G. So assume that for this representation, let's think that this is a multiplication, let's say. But we will see an example. But given B, which is the result of performing the group operation A many times on G, then so in this case, you know B and G. You are asked to find A, and if it is not feasible to find A from this, then we say that this problem is hard. But of course, this problem, the hardness of this problem depends on the group you are working on. So we are saying discrete because we will be working with finite elements. So in this case, most of the time for the multiplication group, we will be working on ZP, which is actually integers modulo P without 0. So let's say an example. So assume that I have chosen a number x, but I'm not telling it to you, and I'm taking the x power of 3 and then perform modulo operation with respect to this number and obtain this. So I'm giving you these numbers. 3 in our scenario, it is the small g, and this number, which is b. So I perform this 3 to the x operation and obtain this number. And now I'm asking you to find x. So this is the hard problem. And as you can see, you cannot answer this question just by looking at it. It is not that easy. But of course, if you take help from a computer, it is not that also hard. You can find it. And the answer is this. So when you put this, you obtain this. So in the worst case scenario, you can perform a exhaustive search or brute force attacks where you try every possible x starting from 1 and take the power of 3, then perform the modulo operation and check if this result is obtained. If it is not, take the next power and so on. So of course, when the numbers are big, then it will take a lot of time to perform this operation. So as you can see, the hardness actually comes from this modulo operation. If you remove it, and as your group, if you just choose the integers, then if I give you 3 to the some secret number powered with the secret number and obtain the result, but not using a modulo operation, then you can take the logarithm of this number with respect to the base 3 and obtain x. So discrete logarithm problem is not hard when your group is integers. But now we are not dealing with the group of integers. We are dealing with ZP, which is actually positive integers modulo P, let's say. So as you can see, it is somewhat hard. And as I explained here, the hardness of this problem depends on the group you are working. So hardness, in other words, intractability of the discrete logarithm problem depends on the group. For example, discrete logarithm on an elliptic curve is harder than the group that I just used here. So this is why there is another area called elliptic curve cryptography, and we will talk about it in the following slides. Okay, so in order to understand Diffie-Hellman key exchange, you have to believe that this problem is hard in this respect. Okay, so of course, trying every possible x is not the best attack. We have some algorithms like polar draw or different methods, but we don't have any sub-exponential type time algorithm to solve this problem. So this is why, especially for the case of elliptic curves, we can use short keys. We will see why this is the case. But again, in order to understand Diffie-Hellman key exchange, you have to believe that this is hard. Okay, you are given 3, this number, and you know the modulo, which is a public parameter, and finding x should be hard. If you assume that it is hard, then we can perform key exchange. So let's move on to Diffie-Hellman key exchange. So algorithm is really simple. It has a very small number of steps. So in our scenario, let's say that A and B want to communicate by using a block cipher like AES, but they don't share the secret key before, and now they want to agree on a secret key, but using an insecure channel. So it starts like this. A picks a random number, small a, and sends G to the A to B. B does the same thing. B chooses a random number B, and then they perform G to the B and sends this to A. A computes, since G to the B is received from B, because B sends this number to A, and small a is a random number that is chosen by A. So A can perform this operation and obtain G to the power A times B. And B can perform the similar thing. They receive G to the A from A, and small b is a number that B randomly chose at the beginning. So B can also compute G to the A times B. So at this point, they agreed on the same number. So this number might be like 10,000 bits, but it doesn't matter. They only need 128-bit AES key, for instance, and they can say that, okay, let's use the first 128 bits of this number and use it as a AES key. So let's see it on a figure and understand why this is secure. So what is, if we perform these operations modulo P using the multiplicative group, then this is what happens. A chooses a random number between 2 to the P minus 2 and computes G to the A modulo B. And let's say that this is represented with capital A. So Alice sends capital A to B, Bob, sorry. And Bob chooses a random number B and computes G to the B modulo P and computes capital B and sends it to Alice. So now B to the A means G to the BA, and A to the B also equals to G to the AB. So they agreed on the same value. So question is, they are sending these numbers, these values using an insecure channel. So can the attacker, by using these values, obtain this secret value too? So let's look at what the eavesdropper can perform. So you are here. In this scenario, the modulo P is a public parameter because Bob or Alice, who is starting the communication, must say that which P they are going to use and which G, which is the generator of the group, they are going to use. So in most cases, these numbers are chosen really small, like 3 or 2 to the 16 plus 1, because it's has a lot of zeros in terms of bits, so the operations are somewhat faster when you chose that G. So the attacker already knows G and P. So when Alice sends A, actually attacker captures capital A. And when Bob sends B, the attacker also captures this. But let's look at the problem. So if the attacker looks at A, this means that they know G, P, and its results when it's powered to with the power A, but they don't know the small a. So the problem is, by knowing capital A, G, and P, can you find small a? And this is actually the definition of discrete logarithm problem. If you can solve this problem in a fast way, then yes, you can get small a. And since you already also listened to the communication and captured B, you can take 8 power of it and capture this. But we assume that discrete logarithm problem is a hard problem. This is why the attacker cannot solve it. So all of the security of our internet communication, almost all of our communications, actually depends on this key exchange algorithm and the hardness of the discrete logarithm problem. So if you can solve this problem in a very fast way, then you can break almost every key exchange between servers and clients and so on. So this is why actually they received a Turing Award, because this allowed us to have e-commerce or e-banking and so on. One problem you need to know is, since as you can see, we need to use very large numbers here so that the discrete logarithm problem cannot be solved by using exhaustive search attacks. And sometimes we are dealing with prime numbers here with hundreds of digits. So implementing this is not a common routine for every programmer. So most of the time people are using open source libraries and so on. So almost nobody implements their own public key algorithms, but they take it from someplace else. So at that point, they need to know how to use it. In my opinion, you should implement it yourself. But anyway, if you don't know that much crypto, at least you should know how it works, because we have seen that even at GitHub you can go and check that people are using this algorithm, but they are choosing G equals to 1, so that the operations are really fast. But if you take G equals to 1, then when you perform all of these operations, you end up with 1. Actually, you're not doing anything. So we are seeing in practice that some companies are communicating by choosing the secret key as 1. Okay, so this is why you have to check how cryptographic algorithms work and how you should choose your parameters.